Morning, Adam. Welcome back. Today we're going to pick up where we left off at the end of the last session. What did we talk about at the end of the last session? Exactly, we were talking about how we can use equations to know how high above the ground an object or a ball. We specifically talked about a ball that's thrown in the air, how high above the ground is with respect or as a function of time. Correct. And what example of such equation can you give me? Or what was the example that I introduced? Correct. It was a quadratic equation. It's not exactly. It started with an h. It was something like h parentheses t. Correct. Then negative 16t squared plus 122. This is the example. Exactly. The example I introduced last at the end of the last session. All right. Perfect. And what does each of these terms mean? It's okay, no worries. It's okay not to remember it. Uh, what if? Let me ask you this: at, at the moment when the object is first thrown in the air, what is the value we use for t? Correct, 0. Exactly. And if I wanted to know, or if I used this t equals 0 in this equation, what will the equation look like now? Correct. H of 0 equal negative 16 times 0 squared plus 122, 0 plus 80. All right, perfect. Yes, exactly. You're right. These cancels out because it's equal to 0 because we're multiplying by 0 as well as this one. Perfect. Now, what does this give me? Gives me exactly. Now I'm left with h of 0 equal 80. And do you remember the unit that we were using for this particular equation for height, feet? Perfect. Now, how do you interpret that result? Those 80 feet, what are they? Correct. So the object was first at the moment of it was first launched. It was 80 feet above the ground. So it was not on the ground. It was 80 feet above the ground. Perfect. So we do get some information that we can translate into a real life setting, right? So the ball was 80 feet above the ground. And you remember where we get this equation from? It's all right, no worries. Uh, this equation comes from physics, and there is an equation that I would like to share with you. It comes from physics, and it comes from this particular equation that we have right here. This equation is widely used in physics to understand the height of an object with respect to time. And notice h 0 here is the starting height, as we discussed earlier. It's the 80 feet that we found for when the time is 0, so at the very beginning. And now if we were to compare this equation right here, the one we have here, to our current equation. So actually, let me do this. Let me scroll this down a little bit. If we were to compare this to our current equation, our current ht negative 16t squared plus 122 plus 8. Okay. What other information can you extract from our equation? by looking at the equation from which is derived, this one, by looking at the description, and by looking at our current equation. Correct. The initial velocity, so the velocity with which the object was thrown in the air, is 122, right? 122. And what's the unit that we said it was for velocity? Feet per second. Perfect. What else? Mhm. Yes. So because what's exactly we have this term right here, the negative 16, that seems to come from the multiplication of 1 over 2, negative 1 over 2 times the gravity. Because what's the value of gravity that we use in the US, in the American system? Yes, the acceleration of gravity is 32 feet per second squared, or feet per square second. Right? Because if I use this 32 feet per square second and I plug it into this, the G you have here, the G we have here, exactly, we will get these negative 16 that we have right here. And do you think that this negative 16 that we have right here will change for all the equations with which we determine height, or will it stay the same? Yes, exactly. It will stay the same because the gravity is has the same value as long as we keep using the same system of units. If you use a different system of units, for example, in another system of units, gravity is 9.8 meters per square second. So as long as you use a consistent system of units, this number in front of t squared will always stay the same. Okay, perfect. Correct. So that's how we get to that equation. Now, what if I wanted to know the velocity of the object in the air? What do you remember about velocity? Yes, it's like velocity tells us the general definition of velocity is the change of distance with respect to time. So how distance is changing with respect to time. Or if we relate it to the height, we can say is how height is changing with respect to time. And but we can also introduce a new concept here. Well, not a new concept, something that we covered in a previous session. It's something that you have done before. Uh, and this is derivatives. What do you remember about derivatives from previous sessions? Correct. Derivatives, they give you the rate of change of something at a given moment, or the rate of change of something with time as well. We can say that, and if we're saying that velocity, yeah, we can call velocity the rate of change of distance with respect to time, but we're also saying that derivatives is the rate of change of something with respect to time or with respect to change of something else. Can we or can we not use derivatives to get velocity in this case? Or we could try it, right? How would you get the velocity here? Since we know the equation with which we get the height of the ball above the ground, what would you do to get the velocity? Exactly. We will take the derivative of that equation. We can say that the velocity with respect to time is equal to the derivative of the height. derivative. This we read this as h prime. That means derivative of h with respect to time. Now, how would you take the derivative of that function for height? That equation that we have for height. It's okay, no worries. I can share some of the rules of derivatives that we could use. Let me put them here. And then if we, let me bring back our equation. Let me see if this lets me copy the equation. No, it's quicker for me to write it. Let me just write it here. So we have this h t equation, height as a function of t. Now, what we want to know is how to take the derivative of this equation, depending on the rules of derivatives. So by looking at that table, these are some of the rules that we discussed when we talked about derivatives. Which rules would you try here first? The sum rule, right? Exactly, because the sum rule is telling you that if you're combining different terms and you want to take the derivative, you can take the derivative of each term individually and then combine them in the end. So at the end of the process. So I can take the derivative of this term first, then of this one second, and this one last, and then I can combine those. Perfect. So now let's do that. So let me write this term right here, 16t squared. How would you take the derivative of that? Which rule would you apply? The power rule. What does the power rule say? Yes, exactly. That one is when you bring down the exponent, you bring it you bring it in front of the variable, and then you reduce it by one. Perfect. Yes, exactly. We can also do that. We can also take the constant number out and simply take, in this case, we're taking the derivative with respect to t. So at the bottom, we write a t instead of an x. That because we have x there in those rules. But in this case, we're taking derivative with respect to t. So we write d of dt. All right, perfect. And you mentioned we take out the negative 16, and that would be derivative with respect to t of t squared. And that is equal to negative 16 times 2. Perfect, yes. And okay, exactly. And we reduce the exponent, we subtract 1 from it. Okay, exactly. So our result would be negative 32t. So this is for the first term. What about the second? The 122t. What would you do here? A similar, yeah, we can do a similar thing. We're taking the constant number out of the derivative, and we can take exactly the derivative with respect to t of t. Okay. All right. So now with this one, which rule would you apply there? We could apply the power rule. Yes. And what's the exponent of this t we have here, of having just t? Correct. It is 1, right? So when we have a variable and we do not see an exponent, the exponent is always 1. Perfect. All right. So what should I write here? So this will be equal to what? 122. Okay, that's a 1. 122 t to the power of 1 minus 1. Yes, so that would be 122 times t to the power of 0. And what is t to the power of 0? What is anything to the power of 0? Correct. That's equal to 1. So it will be 122 times 1, which is just 122. Okay, perfect. Now last we have 80, which is the constant number. Okay, and if we look at those rules there, and we have a constant number, which will, yes, exactly, we will use a constant. And what does that one say? It says that that the derivative of a constant is always 0. So with the derivative with respect to t of 80, that is equal to 0. Perfect. What next? Exactly, we should combine these into into the velocity equation, the velocity with respect to time. Okay, perfect. And that would look like negative 32 t, what else? Plus 122. Perfect. Great. All right. So what if I wanted to know the velocity at 5 seconds after 5 seconds of being thrown in the air? Exactly. We will make our t equal 5. Perfect. Exactly. Um, exactly. We will plug it in. Plug the 5 in the equation. And what will that look like now? B equal 5. Perfect. Equal negative 32. Yes. Yes. Times 5 plus 122. Okay. All right. What next? Now we do the math, right? So we get from here, we will get neg- negative 6, negative 160 plus 122, correct? And that would be, yes. So what's this velocity equal to? Negative 38. And what's the unit? What's the unit of velocity? Feet, feet per second. Correct. Perfect. It is feet per second. Okay. Perfect. All right. So we have covered a lot, but let's notice something here. Notice we got a negative velocity. So what does this mean? What is this telling us? Okay. No worries. Uh, so we our equation from the beginning. Let's say we draw it. Let's say we were to draw that equation. So the height with respect to time. Let's say we were to draw it. Say we were to draw it here. Where the so we will have height over here and time here. So what would that equation look like on a graph? It would look like a parabola, right? Perfect. And where will that graph touch the vertical axis? So what time would that be when it touches the vertical axis? A time equal, yes, t equals 0. So t equals 0 is here. And what's the value of h that we discussed earlier at t equals 0? Exactly. We said The initial velocity was 80. No, my apologies. The initial height. So this is feet. The initial height is 80. And correct. And from here we draw a parabola. We can draw a parabola. It's not gonna be perfect, but it will be something like this. It goes up and then it goes down until it touches the ground. Having a negative velocity means that the object is already on its descending path. It's in the descending portion of this parabola. So it's going down, basically. It's going down. It went up in this first segment. It went up. It reached the maximum height, and then it started to go down. In parabolas, how do we call this point right here? This point of maximum, in this case, would be the maximum height. But in a parabola, well, what do we call that? The vertex. So this will be the vertex. Okay, perfect. All right, so I think we covered a lot today. Um, so the just to recap this last part. So having the negative velocity means that the object is going down from. So it went up, it reached its maximum height, and now it's going down. Now for the next session, I do have some homework for you. It's like a word problem that I have for you. And what you will do, well, you will give it a try. You can text me if you have any questions, of course. You will give it a try, and we will start next session discussing this problem. And in here, what you have to do is find the maximum height and find the velocity of the ball when it hits the ground. Right? Perfect. So, well, it was a pleasure to help you today, and we will see we will see each other next week on Monday. Perfect, at the same time. Great. Perfect, Adam. Have a great day.